Hello guys, welcome back to my channel Gamma Di Gamma. It's been another long break, but summer is coming to an end, for me at least. Can't speak about those of you who are in the southern hemisphere, in Australia particularly. But I have an interesting content for today's video. We're gonna do some explorations. We don't have a particular goal in mind for this video. So there's not one or two integrals that we have to solve or an infinite series. It's actually a combination of them and it's kind of like a natural progression. Well, maybe there is a starting point, there has to be. So consider P to be the product from n equals 1 to capital N. Maybe I can write this a bit better because sometimes it turns out way smaller than I intend it to be. 2 over 1 plus a to the 1 over 2 to the n. So it's basically this term being multiplied with each other. So if we can write some terms to get some perspective, it's going to be 2 divided by 1 plus a to the 1 half times 2 over 1 plus a to the 1 fourth times 2 over 1 plus a to the 1 eighth. And this continues until the nth term. I think that's a little too small, at least the powers is illegible. Okay, so this is the idea. What we can do immediately is factor out all the 2's from the numerator. So that gives us n 2's. So 2 to the n is being factored out like that. And we have a bunch of factors in the denominator. So 1 plus a to the 1 half, 1 plus a to the 1 fourth, 1 plus a to the 1 eighth, 1 plus a to the 1 over 2 to the capital N. So there are these factors. Now, what can we do to sort of simplify this expression or to basically evaluate this finite product in this case? One hope for us, looking at the factors, maybe I can bracket them suggestively. One thing we can do is we can try to use a difference of squares identity because there's a successive squaring, or in this case halving or rooting of terms. So maybe we can use some of that property. So what I can do is I can multiply 1 minus a to the 1 half in the top and in the bottom. And if you don't see how that's going to help, you will see that in a moment. And then alongside that, I will also multiply 1 minus a to the 1 fourth in the numerator and the denominator. Maybe we can do that for the 1/8 term as well. I usually write just two terms if we want to sort of use an infinite product representation, but in this case I just seem to have followed the usual textbook convention of writing three terms and then the last term. It doesn't matter. And then of course the very last term, will be 1 minus a to 1 over 2 to the capital N. And maybe I can write this down here because there's less space to work with. 1 minus 1 plus a to the 1 over 2 to the n, 1 minus a to the 1 over 2 to the n. I apologize if the powers are a little illegible. This is all the space I have. Now, how is that helpful? That's helpful because we can keep the numerator as it is. I have forgotten the dots. Maybe I will rewrite this in a slightly better way. And then what happens in the denominator, and this was the purpose of introducing these additional terms everywhere, is the 1 plus a to the 1 half and 1 minus a to the 1 half will be a difference of squares identity. So it's going to be 1 minus a to the 1 half squared. So that's going to be 1 minus a, just that. 1 minus a to the 1/4 and 1 plus a to the 1/4. We have to square that. That's multiplying the power by 2. So 1 minus a to the 1 half. This is just difference of squares identity applied on these successive pairs of terms. And then the last term, 1 minus a to the 1 over 2 to the n minus 1 in the power. So what this allows us to do is have this entire thing telescope finitely, of course. And so the 1 minus a to the 1/8 will cancel with this successive term, while this will cancel with the preceding term in the numerator. So all we're left with is these two terms that remain from this telescoping product. We have 1 minus a to the 1 over 2 to the n divided by 1 minus a in the denominator, and that's what this infinite product should evaluate. This finite product should evaluate to. But what if we took the limit as n goes to infinity? Well, I'm certain we can allow that, and we can see the limit exists. So let's take the limit as n goes to infinity of sum from n equals 1 to capital N 2 over 1 plus a to the 1 over 2 to the n, and I have to use a small n for indexing. Yes, I haven't messed that up in the original writing. Okay, so we have this. Can we take the limit? Let's see. The limit as n goes to infinity 2 to the n 1 minus a over a to the 1 over 2 to the n over 1 minus a. Well, what can we do? We can probably do a change of limits right here. So let's see. Let's say u is 1 over 2 to the n. That means as n goes to infinity, u will go to 0, giving us, this is p infinity. So p infinity is just limit as u goes to 0, 1 minus a to the u over 1 minus a divided by 2. We can sort of suck out a minus sign from numerator and denominator. So compensate for that. A to the u minus 1 over u times 1 over a minus 1. I've just compensated with minus sign in the numerator and the denominator. Limit as u goes to 0. Now what is this quantity that depends on u as and we're taking the limit? You can do L'Hopital's rule, but if you know for some formulas from your limits 101 calc class, you'll recognize this immediately as the natural log of a and then divided by a minus 1. So it is truly finite if a is not equal to 1. And of course a can't be negative because natural log will sort of mess up. So a is not equal to 1 and a is greater than 0. So we should have these sort of conditions in place, and then it converges nicely in the infinite limit. So yeah, that is really a great result. Maybe I can write it down quickly. because these things are really going to be useful for us moving on. So sum from n equals 1 to infinity 2 over 1 plus a to the 1 over 2 to the small n, I keep messing with the two n's, equals natural log of a divided by a minus 1. It is really nifty. And now if a equals 2, because that satisfies the criteria that it's not equal to 1, it's greater than 0, we're going to have the formula 1 plus 2 to the 1 over 2 to the n being equal to natural log of 2 over 2 minus 1, which is 1. So there's natural log of 2. We have an infinite product representation for the natural log. Well done, guys. Now what if we started our summation from, maybe I should star these. What if we started our summation from 0? Well, no sweat. All you do in that case is basically explicitly write down the 0 term and then multiply that with, the product from 1 onwards. So the 0 term is 2 over 1 plus a precisely times product from n equals 1 to infinity of 2 over 1 plus a to the 1 over 2 to the small n. And we know what the second quantity is. It's precisely natural log of a over a minus 1, which yields 2 times natural log of a over a squared minus 1, which can also be written as, is unnecessary, but natural log of a squared over a squared minus 1. So you see, when we started from 1, we had natural log of a over a minus 1. We start from 0, the a just gets squared. So if a squared over a squared minus 1. So that's, I don't know, it's probably just a coincidence, but it's certainly nice to, notice this pattern with these things. Now moving on, we can really apply these starred formulas, and that was the reason I'm going to call this video Explorations, is because, okay, we had a starting point, this product, and now we're going to sort of explore what this product can do. Maybe, put it inside some integrals or something. Spoiler alert again. Okay, so now speaking about applications, and we love integrals on this channel, don't we? My bad. Integral. This should be considered a sin. Saying sum instead of integral. Integral from 0 to 1 of, let's say, 2 over 1 plus x to the 1 half. 2 over 1 plus x to the 1 fourth. 2 over 1 plus x to the 1/8. And so on, dx. If you want to make this more scary, more intimidating, what you can do, and that is often the case in math, you can make this a square, like a radical. So the 1/4 is going to be basically nested radicals like this, and the 1/8 is going to be this pretty triple radical. So you see the intimidation factor is kind of, multiplied by twice along with this. It's already a infinite product, and then we're also, nesting the radicals in like this. But no need to worry. All we need to do is write this in a more compact product form and identify it with one of those formulas we have. So 2 over 1 plus x 1 over 2 to the n, because we're starting with a square root with a 1/2 power, not just simple x. Now what this allows us to do is integral from 0 to 1 minus natural log of x over 1 minus x. We know this from our formulas above. On top we had a minus 1 in the denominator, so we would have had an x minus 1, but I'm taking the minus outside like this. Fair enough. I can sort of use a property of, upper bound plus lower bound minus x. So x changes to upper bound plus lower bound minus x. So that's 1 minus x. And that keeps the integral completely invariant. I can use that to have natural log of 1 minus x over x dx. This is a property, guys. People have been complaining, you didn't substitute right. I mean, it's just a property. I'm choosing to skip lots of steps so that I don't have to make long, lengthy videos explaining every single thing. So I can use the Taylor series for the natural log. So I'm going to have some integral from 0 to 1, x to the n minus 1 dx. This is just quick, fast tracking everything. We've done a million of these in the past. I might have even done an exact same integral while I was starting the channel off, but this just ends up with the Riemann's zeta function overall integrated. Okay, that's nice. Pi squared over 6, Riemann zeta of 2. You might have memorized this by now, especially after that talk I gave at Cornell. Yes, be sure to check that out. It's long, but it's interesting if you pay attention. And don't doze off. Fortunately, I myself would find it kind of annoying to watch my talks again, but that's just me. And maybe people have a tendency to hate their own voice. Another integral, 2 over 1 plus x, 2 over 1 plus square root x. So maybe I can use the radical form now to scare a few people. And then, well, dx. And now, of course, compact product representation. So sum from n equals 0 to infinity. 2 over 1 plus x to the 1 over 2 to the small n. I just need to keep checking if I don't make that error of writing capital N place of small n everywhere. Maybe I should. That's why people choose the index I. But there's no issue in either way. We know what this is according to our formulas that we derived. 2 times natural log of x over x squared minus 1 dx. What we can do is we can quickly, and I'm going to skip lots of steps, just write this 2 by adding a minus as x plus 1 minus x. Where did that additional minus sign come from? It came from the denominator, which I will choose to write as 1 minus x times 1 plus x. Why is this form important of decomposing? Because I said it, partial fraction decomposition on two terms that this will generate out of factorization for their denominator. Minus integral from 0 to 1 natural log of x over 1 plus x dx. Well, I exactly did the first integral, evaluated it to be pi squared over 6 minus natural log of x. I can use integration by parts. So I'm getting a product of these natural logs evaluated from 0 to 1 plus integral from 0 to 1 natural log of 1 plus x divided by x dx. Well, you can check this goes to 0 at both cases. The 0 case, you probably need L'Hopital's rule. 1 case is pretty trivial. Now we're going to get pi squared over 6 plus Taylor series expansion right away. No time wasted in unnecessary explanations. You guys must be fluent with all this kind of manipulation by now. Or if you aren't, watch previous videos, take a piece of paper, try it out. Always good practice to practice yourself. Sum from n equals 1 to infinity minus 1 to the n plus 1 over n squared, which is the Dirichlet eta of 2, by the way, which will be pi squared over 12. I've derived this before. Or you can relate it to the Riemann zeta by this nice identity they have of, I think 1 minus 2 to the n minus 1 or something like that, which is like a common factor between them. And there we go. That's pi squared over 6. And that should, be good content for probably one more week or so until I get my feet back in the US in Cornell, and then maybe I can start some new topics, start teaching a little more physics maybe than I have in the past. So peace out. Please subscribe to my channel. Without you, this will not be possible. I need more support so that I can monetize, and then maybe I can introduce some animations once I have some semblance of a team in the near future. So thank you for everything and peace out. Stay tuned for more content.